Hello everyone, I'm glad to be here to show this work. This work is realized by our work study student, Timothé, and I will talk about leaf rendering, foliage rendering. Rendering vegetation remains a challenge nowadays. We render a lot of forests in video games or, for example, in visual media. And nowadays, it's used more and more in agricultural simulation to have digital twins about plants for study behavior with condition environment and understand thicknesses or cell structure of the plants and leaf. Rendering vegetation, leaf, or foliage is not new. In previous decades, a lot of work are published. All of this work could be grouped into 4 ways. First one, practical model. Just the main goal of practical model is render with beautiful color and with efficient computations. The second way is physical-based rendering, where we want to integrate in the rendering spectral data to have physical reflectance and transmissions. The third way is bio-inspired model with radiative transfer model, where we want to modelize correctly the structure of a leaf to make rendering and base the color computation with the pigment concentrations with different models like place model. And the last way is edging models. In our case, we want to simulate leaf rendering for agriculture simulation, and we need edging models for integrate time dimension in our modelization and our simulation. And we want to be close of biology to have right behavior of a leaf. So, if we look quickly at the structure of a leaf, at the anatomy of leaf, we have different layers perceptible. For example, upper epidermis, palisade mesophyll, vein, etc., etc. We want to use an optical model with efficient computation, so we want to simplify this model. So we abstract each part of our leaf with plates, and we accumulate a stack of plates to simulate our rendering. And with this stack of n plates, we compute our reflectance, transmission, and absorptions. With this model, it's easy to extend to spectral dimensions. We can compute all reflectance, transmission, and absorption along the wavelength dimension. In this work, we focus mainly on the visible spectrum, but it's easy to extend to a near-infrared to study, for example, the cell structure in our plants. One model is very interesting in this bio-inspired model is prospect family models proposed by Jagbu et al. In 19. They extend place model to represent the leaf, and they consider a leaf as a plane parallel rough transparent plate with refractive index and absorption coefficients. This family of models extends the place model to simulate leaf spectral properties as a function of pigment, water, and dry matter. So we integrate biology elements to make our rendering, and they propose formulation to computation, reflectance, and transmittance and absorption with these informations. Just, it could be noted the n parameter is not directly the number of layers in our leaf. It's just a structural parameter. It reflects the internal complexity of the leaf. So we integrate concentration of each pigment. For example, in your leaf, we consider 3 pigments in particular: chlorophyll, carotenoids, and anthocyanins. And we integrate to water and dry matter by coefficients in the computation of absorbance. At right, you can see just a little comparison between a measure value with curve line, the blue curve, and the estimation done with prospect models. We can see that the result of prospect is very close of the ground truth, and that is very interesting for us. So we propose a method to use this family of models to approximate the rendering of a leaf in a spectral rendering here, Mitsuba 3. Our model, our pipeline is simple. We have different data to begin. We have leaf optical properties, just measure data about the leaf we want rendering. And we have the leaf albedo. We propose a first application, leaf materialize, to extract different information with this data and create a leaf profile. And the leaf profile will be integrated in renderer, spectral renderer. To integrate it in Mitsuba 3, we use just a plugin to integrate the BSDF and the handle of the leaf profile. And after, Mitsuba 3 can render easily a leaf with propositions. Now I will talk about leaf materialize and which data will extract of this different information and how we can construct the leaf profile to have a good and accurate rendering about leaf. Firstly, we need to characterize the concentrations of each pigment. So we need 3 curves along the life cycle of a leaf for example, chlorophyll. But when you measure and when you use actual data set about leaf, you don't have enough of point to interpolate correctly all data. So we do a simple approximation with a Gaussian formulation to have a smooth rise and smooth decline. And we compute these Gaussians for each pigment along the life cycle of our leaf. And with that, we can compute correctly with previous formulations the color of the leaf along the life cycle. And we can integrate the time dependence. So if we look this picture at the tiers of, so on the first part of the leaf rendering, the leaf is very green. And when the end of the life cycle, the color is very red. In a foliage, each leaf does not have the same time because when you are far of the plants, the base of the root, you are younger, and when you are soon close, you are younger. So to integrate this, we have add easing functions to remap time for each leaf in the foliage. The main goal of this function is just add a variation of temporal for each leaf. Actually, this function is randomly, but in future way, we want to constrain this with positional features on the leaf, on the foliage. From the leaf albedo, we extract different information, for example, leaf mask to compute edge distance map. And we compute a vein mask in parallel to compute a vein distance map. The interest of these two maps is to merge into the temporal offset map. The goal of these features is just to describe which part is younger or older in the same leaf. So with that, we can have an heterogeneous rendering of a leaf with different temporal aspects. And we propose just a BSDF to make rendering. This BSDF is proposed in two parts. diffuse part with a proposition of prospect model, where we have a spectral numbation, reflectance, and transmittance, driven by biophysical pigment parameters. And we have a specular term, GGX microfacet model, to reproducing epidermal highlights. And with all this contribution, we can compute different color of the leaf based from the biology inspirations. Here you can see a comparison between chlorophyll concentration and carotenoids and anthocyanin concentrations. So we can see if our chlorophyll may have high concentration in our leaf, the color of the leaf is green. And if we reduce chlorophyll concentration and increase carotenoids or anthocyanins concentration, our leaf is red or brown. With the time offset map, we can have an heterogeneous rendering. Here, with this picture, you can see close of the vein a younger part with more concentration of chlorophyll, and where you're far of the vein, you have an other color because you have less of chlorophyll concentrations. Now you can see a video to demonstrate aging of agricultural pastoral area for grab plants. At the beginning of the video, plants is very green, and at the end of the video, you have less of chlorophyll, so the plants become red. Now you can see a comparison of simulation at left and a photo at right. We have a similar aspect around appearance in our simulations, and with this picture you can see the easing function effect. If you look, I tried it. Here, for example, you have a leaf green on the same plant, and you have a red leaf because we have remapped all of the time of each leaf in the foliage. And with the simulation, the interest, one advantage is to change, for example, the point of the day and illumination as you want. In conclusion, we propose a pipeline to render leaf and foliage with time dimensions integrated, and we have a solutions based on prospect model to have a trade-off between physical interpretability and computational efficiency. And this solution allows us to have visual and spectrally plausible aging effect as pigment degradation, translucency variation, surface reflectance changes, etc. In future works, we work on the acquisition of a lot of data, and along 1 year with regular acquisition, for example, each day, in the controlled environment. The goal behind this is just to have a digital twin of grab plants, for example, in our case, with a lot of measured data about this plant with the same plants, because actually in your dataset, we use different plants along the years to get the data. This work have to objective to simulate this plant and work and understand the sicknesses and diseases of climatic variability, this effect on the plants. Yep. Thank you.
So we have time for some questions. Are there any questions from the audience?
Thank you for the intriguing presentation. One question I have as somebody who's got gardening as a hobby. Plants age, and that doesn't just mean the leaf color changes, but the leaf shape changes quite a bit because it grows in size, and then once it starts to yellow, at least the periphery of the leaf starts to curl up, which will, I mean, I presume this has applications in remote sensing, so you'll be interested in the aggregate reflectivity of the whole vineyard based on leaf age, where the shape of the leaf will actually also make a difference. Have you done any estimation? I mean, it's really hard to say how much of an effect it will have. Did you do any estimation of how large that impact is going to be?
They have a lot of impact on the geometry of the leaf, but we don't have enough of data to simulate this. That's why our future work is to measure, for example, the deformation of the geometry of each leaf for one plant. Actually, just we consider the aging of the leaf, and that's all.
Thanks for the presentation. I have two questions. The first one is, how did you get the pigment degradation data? Did you measure, or it was?
To get the concentration of each pigment?
Yes.
Just we measure that, we use a data set, biology data set about this.
Okay. And what do you think, the second question is, so you show this structure with layers, and then, okay, you have the diffuse, and then you have the spectral curves. So what do you think about like trying to simulate this, trying to create the structure inside? You know, the layers, they were kind of like a porous inside, so there was like a spongy material in one of the sketches that you show.
Can you repeat?
At the beginning, there was a sketch of like layers with the structures and so on. No, but not this one, because this one is already the abstract version. The sketch from the, I think it was before, like the sketch from the domain field, no? Because this one is the optical model already. You know, there was a sketch where you have like the layers, and then the layers there were...
the interaction between each layer?
Yeah, but the before, can you go to the slide before?
Yep.
Yeah, exactly, this one. So if you see the left, the model is definitely more complex than the right one. So
yes.
What I was thinking is, you see the spongy mesofield, you approximate this as a diffuse, and with the measurements of the reflectance and so on. What about like trying to do the simulation of, you know, try to get this reflectance curve? Do you think it's yes, exactly. Something like you do the wave simulation, and then you get the...
Yes, we have a difference because we want to use an efficient model for reduce the computation. So we consider each layer is the same in our stack. Mm-hmm. That is an approximation and not the ground truth, for example. That's why we can have a difference in the computation of the curve, because we have an approximation, so we accept a little error on this.
Yeah. But the approximation is quite good, no?
The approximation is orange.
No, the approximations are good.
Oui?
The approximations are good.
Hmm? Yeah. No, it's close. It's close. But if we look here, you have a little error. You can see.
Thanks.
I wonder if your specular layer is only at the top. Is there also specular at the bottom? And you have so the specular is for the epidermis, and there's upper and lower epidermis. So your specular layers are the both on top and at the bottom.
The specular is just on the top.
So
and
if you look from the back of the leaf, you don't have the specular layer.
yes, because specular is just the direct reflections of the light on the granula. And if you look the leaf at the bottom, you can see the transmissions, and that's all. You don't have a specular effect on this.
And how does the layering work from the back side?
I don't know.
Maybe we should take this offline because we're at time. So let's thank the speaker again and move on to the next presentation.